Variable type matters because it determines what it even means to summarize the data. A summary statistic is a number that represents the data in a simple way, but different types of variables need different summaries to be meaningful. The main types you will see are binary, two categories like yes, no, categorical, multiple categories like race, group, or department, ordinal, categories with a natural order like mild, moderate, severe, continuous numeric measurements like blood pressure or wait time, count, 0, 1, 2, 3, events, and time to event, how long until something happens. Each type has a different natural language for summarizing, and using the wrong summary can hide the true pattern. Binary variables are usually summarized with counts and proportions. The basic summary is how many are yes and what percentage that represents, sometimes with a confidence interval. Examples include completed the program, had an adverse event, received the service, or was readmitted. A proportion is interpretable because it directly answers how common is it. Multiple examples show the value. 12% readmitted is immediately meaningful. 88% completed is immediately meaningful. When comparing groups, differences in proportions or risk ratios are also natural. Trying to summarize a binary variable with a mean can confuse people because the mean of a 0-1 variable is technically a proportion, but it does not look like one. Saying the mean completion was 0.88 is less clear than 88% completed. Categorical variables with multiple categories are summarized with frequency tables, counts and percentages in each category. Examples include categories like region, clinic, insurance type, job role, or diagnosis category. The most important principle is that categories should be clearly labeled and mutually exclusive so the table adds up cleanly. Multiple examples show how category summaries support interpretation. A table of distribution by region can show whether one region dominates the dataset. A table of insurance type can reveal whether coverage differs across groups, which can matter for confounding and access. For reporting, these summaries are often presented as N% for each category. Sometimes a category summary also includes a missing category because missingness itself can be informative and it helps prevent denominators from silently changing across variables. Ordinal variables are categories with an order, like low, medium, high, mild, moderate, severe, or Likert responses from strongly disagree to strongly agree. Ordinal variables can be summarized with frequency tables like categorical variables, like but their ordering invites additional summaries like medians and percentiles. For example, if satisfaction is on a 1 to 5 scale, the median may be more meaningful than the mean if responses are skewed, or if the scale is not truly interval. Another example, if severity is categorized into ordered levels, reporting the proportion in each level is useful, but you might also report the proportion at or above a clinically meaningful threshold. Ordinal summaries often benefit from cumulative statements such as X% reported moderate or higher because those statements align with the ordering and are often easier for stakeholders to interpret. Continuous variables are numeric measurements where differences are meaningful, like age, blood pressure, wait time, cost, lab values, or test scores. The typical summaries include mean and standard deviation when the distribution is roughly symmetric, and median and interquartile range when the distribution is skewed. The mean is sensitive to extreme values, so it can be misleading when the distribution has outliers or a long tail. The median is more robust, so it often reflects the typical value better in skewed data. Multiple examples show this. Wait times and costs are often right skewed, where a small number of extreme values can pull the mean upward, making the median more representative. Lab values can also be skewed, especially when values are bounded below by 0. Scores might be bounded at both ends, leading to ceiling or floor effects, which can make the mean less informative without additional context. Count variables represent the number of events, like number of visits, number of defects, number of missed appointments, or number of incidents. Counts are often summarized by the mean count per unit, but they are frequently skewed, like with many zeros and a few high counts. That is why medians, percentiles, and the proportion with 0 are often important summaries for counts. Multiple examples make this clear. Many people may have 0 emergency visits, while a small number have many visits. Reporting only the mean can hide that concentration. Similarly, many accounts may have 0 complaints, while a few accounts generate many complaints. A mean alone does not show whether the issue is widespread or concentrated. Counts also often need rate summaries when follow-up time differs. For example, events per person year or events per month are more comparable than raw counts when observation periods vary. Time to event variables are summarized differently because some people do not experience the event during follow-up. This is where censoring matters, meaning you observe that the event did not happen up to a certain time, but you do not know if or when it would happen later. Summaries often include Kaplan-Meier survival probabilities at specific times, median time to event when it is estimable, and event rates over time. Multiple examples show why standard averages fail here. If half the people have not had the event by the end of follow-up, you cannot simply compute an average time to event dense without making strong assumptions. Instead, survival summaries describe the proportion event-free over time and allow fair comparisons across groups with different follow-up lengths. This preserves the meaning of the data and avoids treating not observed yet as never. Overall, variable type drives summary statistics because the summary has to match what the values represent. Binary and categorical variables call for counts and percentages. Ordinal variables often call for distributions and sometimes medians. Continuous variables call for means and standard deviations, or medians and interquartile ranges, depending on shape. Counts often call for mean, median, and zero inflation summaries, sometimes rates. Time to event calls for survival summaries because of censoring. When summaries match variable type, the story becomes clearer and comparisons become fairer. When summaries mismatch, the numbers can hide what matters and can push decisions in the wrong direction. Variable type determines which statistical tools match the data generating process. A model or test is basically a structured way to compare groups or estimate relationships, and it has assumptions about what the outcome looks like. If the outcome is binary, a method that assumes continuous values can give nonsense or misleading results. If the outcome is a count, a method that assumes normally distributed errors can perform poorly when there are many zeros and a long tail. If the outcome is time to event with censoring, methods that ignore censoring can bias estimates. The practical rule is that you pick methods that respect the outcome scale and distribution, not methods that are simply familiar. When the outcome is binary yes-no, common choices include chi-square tests or Fisher's exact test for simple group comparisons, and logistic regression for modeling relationships with multiple covariates. Chi-square tests are often used when you want to compare proportions between groups, like comparing completion rates across groups. Fisher's exact test is often used when sample sizes are small or expected counts are low, because it remains valid in sparse data. Logistic regression is used when you want to adjust for covariates, or estimate how predictors relate to the probability of the outcome. Multiple examples include modeling the probability of an event based on exposure and baseline characteristics, comparing the probability across categories like region or clinic, or estimating how the probability changes with a continuous predictor like age. The key feature is that logistic regression naturally models probabilities through the odds scale, which requires careful interpretation. When the outcome is continuous, common choices include t-tests for comparing means between two groups, analysis of variance for comparing means across multiple groups, and linear regression for modeling relationships and adjusting for covariates. These methods assume the outcome is measured on a numeric scale, where differences are meaningful, and they often assume the residuals behave reasonably, roughly symmetric and not extremely heavy-tailed. Multiple examples include comparing average blood pressure between groups, comparing average wait times across sites, or modeling how a score changes with age and other variables. When assumptions are questionable, alternatives include non-parametric tests like Wilcoxon rank sum for two groups, or Kruskal-Wallis for multiple groups, which compare distributions more generally and are less sensitive to outliers and non-normality. The choice is often driven by how skewed the data are and how much outliers influence the mean. When the outcome is a count, common choices include Poisson regression and negative binomial regression. These models are built for non-negative integers and naturally represent event counts. They are especially useful for comparing rates when observation time differs across people, because you can include an offset to account for different exposure time. Multiple examples include modeling number of visits per person year, number of defects per batch, or number of incidents per month while adjusting for exposure time. Poisson models assume the mean and variance are similar, which is often violated in real data where variance is larger than the mean. Negative binomial models relax that and handle overdispersion, which is common when a small number of units have very high counts. When there are many zeros, additional approaches like zero-inflated models may be considered, but the main concept remains: count outcomes often require count-specific models rather than normal-based models. When the outcome is time to event, common choices include Kaplan-Meier curves for describing survival over time, log-rank tests for comparing survival curves between groups, and Cox proportional hazards regression for modeling associations while adjusting for covariates. These methods are designed for censoring, which means some people do not have the event observed during the study window. Multiple examples include time to readmission, time to relapse, time to completion, or time to resolution. Kaplan-Meier curves show the proportion remaining event-free over time. The log-rank test compares the curves in a way that accounts for censoring. Cox regression estimates hazard ratios, which compare event rates over time between groups, under assumptions that need checking. The design implications matter here. Time to event analysis is most appropriate when follow-up time varies or when censoring is substantial. Predictor variable type also matters, even when the outcome is fixed. Categorical predictors are usually represented with indicator variables, which allow the model to estimate differences by category relative to a reference category. Ordinal predictors can be treated as categorical or can be modeled with a single ordered effect, depending on whether equal spacing is a reasonable assumption. Continuous predictors can be modeled linearly, but if the relationship is not linear, you may use flexible approaches like splines. Multiple examples include modeling risk across age, where risk may accelerate at older ages, or modeling effect of dose, where effects may plateau rather than increase indefinitely. Treating a continuous predictor as categorical can lose information and reduce power, while treating a categorical predictor as continuous can impose unrealistic structure. The choice should follow what the variable represents. Data structure also influences test and model choice, not just variable type. If you have repeated measures, you need methods that account for within-person correlation, such as mixed effects models or generalized estimating equations. If data are clustered within sites, you need cluster-aware methods such as multi-level models or cluster-robust standard errors. If data are time series, you may need methods that account for autocorrelation and seasonality. Multiple examples include repeated symptom scores over weeks, outcomes clustered within clinics, or monthly rates over multiple years. In each case, a simple t-test or ordinary regression that assumes independence may give overstated precision. This is why type drives test choice is true, but it is incomplete unless you also consider dependence and clustering. Finally, the choice between tests and models is guided by your goal: comparing groups, estimating adjusted effects, predicting outcomes, or describing relationships. Tests are often used for simple comparisons and can answer, is there evidence of a difference? Models are used to estimate the size of relationships, adjust for covariates, and generate predicted values. Multiple examples show the difference. A chi-square test can say whether completion differs by group, while logistic regression can estimate adjusted differences and explore how completion changes with multiple predictors. A t-test can compare average wait time between two processes, while linear regression can adjust for day of week, staffing levels, and site. The variable type tells you what tools are appropriate, and the research question tells you which tool is most useful. Transformations are ways of changing how a variable is represented, so it better matches the analysis goal, improves interpretability, or better fits model assumptions. Transformations are not about making the data look nice, They are about aligning measurement with meaning and aligning distributions with methods. Many variables in real datasets are skewed, have outliers, have natural bounds, or are recorded with inconsistent units. Transformations help address these issues while keeping the interpretation honest. Examples include converting a continuous measure like cost to a log scale, collapsing detailed categories into a smaller set, creating a binary indicator from a continuous measure based on a meaningful threshold, or converting raw counts into rates using a denominator. Binary variables are often transformed from more complex raw information into a clear yes-no indicator. This is common when raw records are event-based and you need a person-level indicator. For example, multiple encounter records might be transformed into had any hospitalization during the period. Another example, session records might be transformed into completed at least one core module. A third example, documentation fields might be transformed into meets standard versus does not meet standard. The key risk is that binarizing can throw away information, so it should be done when the decision truly depends on a threshold or when simplicity is needed. When there is value in intensity, you might transform into ordered categories instead of a binary, such as none, some, or full completion. Categorical variables are often transformed by recoding, collapsing categories, or creating a reference category that supports meaningful comparisons. Collapsing is common when some categories are sparse because very small cell counts make estimates unstable and can create privacy or interpretability issues. For example, detailed job roles might be collapsed into broader role families. Another example, small geographic categories might be combined into regions to produce stable rates. Another example, a detailed diagnosis list might be collapsed into clinically meaningful groups. Another common transformation is releveling, meaning choosing a reference category that makes interpretation clearer, such as using the most common or most policy-relevant category as the comparison. Categorical transformations should be guided by meaning first, and then by statistical stability. Ordinal variables can be transformed in multiple ways depending on what you need. One option is to keep all categories and analyze them as ordinal outcomes, which respects ordering. Another option is to collapse adjacent categories, such as combining strongly disagree and disagree into a single disagree group, especially when sample sizes are small or distinctions are not important. A third option is to create a threshold indicator, such as moderate or higher versus below moderate, when the decision hinges on identifying a meaningful level. Examples include collapsing a 5-point satisfaction scale into 3 levels, low, neutral, high, or turning severity categories into a binary that reflects clinically meaningful severity. The trade-off is always between detail and stability. More categories preserve nuance but may create sparse cells. Fewer categories simplify interpretation but can hide gradients. Continuous variables are frequently transformed to address skewness, outliers, and nonlinear relationships. A very common transformation is the logarithm for variables like cost, income, and wait time when they have a long right tail. Log transformation compresses large values and can make relationships more linear and residuals more stable. Examples include modeling cost on a log scale to avoid a few extreme costs dominating the fit, modeling time to completion on a log scale when some units take exceptionally long, or modeling lab values that are naturally multiplicative rather than additive. Another approach is standardization, such as converting a variable to a z-score, which measures how many standard deviations a value is from the mean. This can help compare effect sizes across predictors and stabilize numerical fitting. A third approach is using splines or piecewise terms to capture nonlinear patterns without forcing a straight line, such as allowing age to have a curved relationship with risk. Count variables are commonly transformed into rates by incorporating a denominator or an exposure time. This is essential when people or units have different opportunity for events to occur. For example, number of incidents per 1,000 hours worked is more comparable than raw incidents when hours differ. Another example, number of visits per person year is more comparable than total visits when follow-up time differs. Another example, number of defects per batch size is more comparable than total defects when batch sizes differ. Counts are also sometimes categorized, especially when there are many zeros, such as transforming a count into 0, 1, 2 plus to simplify interpretation and reduce skew. Another transformation is truncation or Windsorization, which limits extreme values. This must be used carefully because it changes the data and can hide meaningful high-burden cases. Time-to-event data are often transformed by defining the time origin, the event indicator, and the censoring rule in a consistent way. The transformation is not just mathematical, it is conceptual. For example, you might transform raw dates into days from baseline to event and an indicator for whether the event occurred within follow-up. Another example, you might transform multiple possible event definitions into a single composite endpoint, such as first occurrence of any of several outcomes, when that matches a decision context. Another example, you might transform the outcome into a fixed time binary, such as event within 30 days, when a simple window is the priority and follow-up is consistent. These choices determine whether survival analysis is needed and how results should be interpreted. Finally, transformations often include building derived variables that represent meaningful constructs more directly than raw fields. Examples include creating a comorbidity score from diagnosis history, creating a baseline utilization measure from prior events, creating a socioeconomic proxy from area-level indicators, or creating an adherence measure from refill patterns. Derived variables can improve confounding adjustment and interpretability, but they also introduce assumptions. For example, a comorbidity score assumes certain conditions reflect baseline risk in a particular way, and an adherence proxy assumes certain refill patterns reflect actual use. Good practice is to document how derived variables were created and to treat them as measured constructs with limitations, not as perfect representations of complex reality. A major pitfall with binary outcomes is mixing up what the number represents and what comparison you are actually making. A percentage answers how common, but it does not automatically answer how much better unless you specify the comparison and the denominator. For example, saying 20% had the event is descriptive, but the event was 5 percentage points higher in group A than group B is a comparison, and those are not interchangeable. Another common pitfall is treating an odds ratio as if it were a risk ratio. In many settings, an odds ratio can look larger than the actual change in probability, especially when the outcome is common. For example, an odds ratio that sounds like double can correspond to a smaller change in probability depending on baseline risk, and that can lead stakeholders to overestimate impact. A third pitfall is ignoring the difference between person-level and event-level binary outcomes, such as person ever had an event versus visit had an event, which can radically change the meaning of results. Categorical and ordinal variables bring pitfalls related to categories, ordering, and sparsity. With categorical variables, the most common mistake is comparing categories without a clear reference group or without realizing categories are not comparable due to different base sizes. For example, counts across categories can mislead if one category is much larger, and percentages can mislead if the denominator changes from one comparison to another. Another pitfall is sparse categories that create unstable estimates, where a small number of observations can produce extreme-looking effects that do not generalize. For ordinal variables, a frequent mistake is treating the scale as if it has equal spacing when it may not. For example, the difference between agree and strongly agree on a survey is not guaranteed to be the same as the difference between neutral and agree. So using means without context can imply precision that the scale does not support. Another pitfall is collapsing ordinal scales in a way that hides important gradients, such as turning a 5-level severity scale into a binary variable without a clear reason, which can erase meaningful middle range variation. Continuous variables commonly fail when summaries or models ignore skewness, outliers, and natural bounds. A classic mistake is reporting only the mean and standard deviation for a distribution that is strongly Another pitfall is interpreting a coefficient as if it applies equally across the full range when the relationship is nonlinear. For example, a 1-unit increase might have a strong association at low values and a weaker association at high values, so a single linear slope can hide curvature. A third pitfall is ignoring measurement units and meaningful scale, such as modeling a variable in raw units that are too small or too large, which can make effects look tiny or huge purely because of how the variable is scaled. Count and time to event outcomes have pitfalls that often come from ignoring exposure time and censoring. For counts, a common mistake is comparing raw counts when the opportunity for events differs. For example, comparing number of incidents across sites without accounting for hours worked will unfairly penalize higher volume sites, and comparing number of visits across people without accounting for follow-up time will make people observed longer look like they have higher utilization, even if their rate is the same. Another pitfall is using a method that assumes a symmetric distribution for counts that are zero-heavy and highly skewed, which can create unstable or misleading results. For time to event, the biggest pitfall is ignoring censoring and treating no event observed as if the event never occurs. This can bias comparisons when one group has shorter follow-up, different dropout patterns, or different observation windows. Another common pitfall is interpreting time to event results without stating the time origin and the follow-up rules, which makes it unclear what time actually means in practice. Coding and recoding conventions are the rules you use to turn messy, real-world values into consistent, analysis-ready variables. This includes how you represent categories, how you handle unknown and not applicable, how you set reference groups, and how you document every decision so results can be reproduced. Conventions matter because many variable types look simple, but arrive in inconsistent forms, such as different spellings, mixed capitalization, multiple versions of the same category, or values that mean different things in different contexts. For example, the same concept might appear as male, wem, one, or man, depending on the source. Another example, a missing value might be truly unknown, or it might mean question skipped, or it might mean not asked, and those are not the same. Coding conventions prevent those inconsistencies from silently changing your denominators and your conclusions. For binary variables, a standard convention is to code them as 0 and 1, where 1 indicates event occurred or yes, and 0 indicates no. This seems straightforward, but the key is consistency and explicitness. For example, if a survey question has values like yes, no, refused, and blank, you need a rule for whether refused and blank become missing or whether they become no, because that choice changes the estimate of the proportion. Another example, if a service record contains multiple fields that imply service delivery, you need a rule for which field is authoritative and how to code conflicting evidence. A third example, if the outcome is any event, you must define whether multiple events count the same as one event for the person-level indicator. A consistent binary convention also helps interpretation in models because coefficients can be translated into differences between 0 and 1 groups. For categorical variables, Sliventions usually focus on category labels, grouping rules, and reference categories. A good convention is to create mutually exclusive categories that cover all observations and include an explicit category for missing or unknown when appropriate. For example, if insurance type is recorded as many detailed codes, you might group them into a stable set of categories that are meaningful and not too sparse. Another example, geographic variables often need a consistent naming convention so that St. Louis and St. Louis do not become separate categories, or so that city and county labels do not create duplicates. A third example, job role titles might need standardization because people enter them differently over time. Reference category choice is also part of convention. You should pick a reference group that makes comparisons interpretable, such as the largest group, the current standard, or a policy-relevant category, and keep it consistent so interpretation does not shift across models. For ordinal variables, coding conventions should respect the ordering. A common convention is to map ordered labels to ordered integers in a way that matches the true direction, such as 1 equals lowest and 5 equals highest, and to document that mapping clearly. This avoids the mistake of reversing the scale, which can flip interpretation. For example, if a satisfaction scale is coded so that 1 means strongly agree in one dataset and 1 means strongly disagree in another, combining them without recoding will create nonsense. Another example, severity categories might be recorded as text in one system and as numbers in another. You need a convention that produces a consistent ordering. Ordinal conventions also include decisions about collapsing categories, such as combining rare top categories into a single high group, and those decisions should be documented because collapsing changes what the variable represents. For continuous variables, coding conventions focus on units, ranges, outliers, and missingness. A key convention is to standardize units before analysis because as unit inconsistencies can create extreme values that look like real outliers. For example, height might be recorded in inches in one system of frontes and centimeters in another, or weight might be recorded in pounds versus kilograms. Another example, costs might be recorded in dollars in one data set and cents in another, which can create a 100-fold difference if not corrected. Range checks are another convention. You define plausible ranges and decide what to do with values outside that range, such as setting to missing, flagging them for review, or correcting clear formatting errors. A third convention is how to treat rounding and precision, such as whether to keep decimals, whether to round for reporting, and whether to use consistent decimal places across outputs, so comparisons are clear. For counts and time-based variables, coding conventions often involve defining what counts as an event, how to handle duplicates, and how to define time windows. For counts, you need a clear rule for whether multiple records represent distinct events or fragments of the same event. For example, multiple line items in a single encounter might represent one encounter-level event, not multiple events. Another example, multiple transactions within a short window might represent one episode rather than repeated episodes. For time variables, conventions include defining the time origin, defining the follow-up window, and handling incomplete dates or times. For example, if only the month is known but not the day, you need a convention for how that gets represented because time to event analysis depends on accurate timing. Another example, if a system changed how it records timestamps, you may need a convention for harmonizing time variables across the change. Across all variable types, the most important convention is documentation. Documentation means keeping a clear mapping of raw values to clean values, recording recode logic, and maintaining stable definitions across refreshes so trends are real and not artifacts of changing coding rules. For example, if you change how you group categories halfway through a time trend report, the apparent trend can change even if the underlying reality did not. Another example, if unknown is treated as missing in one report and treated as no in another, the metrics will not be comparable. A third example, if you rename categories without keeping a lookup table, you can break reproducibility and make it difficult to audit results later. Strong coding conventions are the foundation for clean denominators, stable dashboards, and analysis that can be trusted across different settings and jobs.